All right, so today we're going to be looking at this idea of thermal expansion. We know that when certain materials, we're going to look at gases more in chemistry really, but really when we're looking at solids and liquids, we know that when things heat up, they tend to expand. We see this with the roads on hot summer days. When the concrete tries to expand, doesn't have room, and it ends up buckling the road, making driving dangerous. Uh, Physicists actually have an equation to figure out just how much uh, a material will expand. They've also figured out, we also know that different materials change size, differently, and that's based upon some chemistry, some intermolecular forces, stuff like that. Um, so you are going to need to kind of look up a table of coefficients of thermal expansion in order for this video to make sense, in order to kind of do the practice problems. So the equation we're going to use is, so over here, I'm looking at delta L, or the change in length, is equal to, so here we have that alpha character again. This time, alpha is going to stand for the coefficient, sorry for the writing there, got really, really small, of thermal expansion. Now this point right here, this is the part that's going to be different for every single substance. Concrete, expands by a certain amount per change in temp. Aluminum, brass, silver, even glass will change size based upon changes in temperature. So this one, though, is just a set number. You just have to get from a reference chart, reference table, anything like that. Capital L, little I, that's our initial length. And this last part here, delta T, big T, that's our change in temp. For the most part, the coefficient of thermal expansion, typically, it'll be given to you as either the inverse of Kelvin or kind of a inverse of Celsius, so 1 over K or 1 over C. Keep in mind, though, a change in 1 degree Celsius is also a change in 1 Kelvin. So it doesn't matter what unit this is in, it's not going to change the number at all. So change in length, meters, initial length, meters, change in temp, degrees Celsius, or Kelvin. Um, it's going to be one of those two. And to convert between the two, like if you have Celsius, you just add 273.15 to get to Kelvin, depending upon what the question's asking for. So looking at this in practice, let's say that I have we're going to pretend that that is a 3-meter long tube or rod of aluminum. And I apply a certain amount of heat to it. And let's say that we're going to change its temperature from, let's go 25 degrees Celsius, and we're going to change it up to, let's go big. Let's say that we get it up to 115 degrees Celsius. So we get it over the boiling point of water there. And I'm going to check a sheet real quick, and I'm going to find out that aluminum has a coefficient of thermal expansion of, checking the sheet here, it looks like it's 24 times 10 to the negative 6. It is a really, really small number. And then that's 1 over degrees Celsius there. Okay. So 24 times 10 to the negative 6, that's the coefficient of thermal expansion for aluminum. And we figured out that my aluminum rod here, starting with an initial length of 3 meters, to find my change in temp, I'm going to take 115 minus 25. And if memory serves me right, that should be 9 degrees Celsius. Remember, change just means final minus initial. So let's ask the question. what's the new length of the new rod? Okay. I want to know what's the final length of that aluminum rod. Well, in order to find the final length, I'm first going to have to find the change in length. And to do so, I know that change in length is equal to the coefficient of thermal expansion times the initial length times the change in temp. So now I already figured out what these numbers are. So in this case, the coefficient of thermal expansion is 24 times 10 to the negative 6. I'll go degree C, -1. Keep in mind, this is a number. Essentially, it's almost in scientific notation. What I like to do, though, with those numbers, I just throw in parentheses, just in case I ever have to divide by that. So then I have, so that's my coefficient of thermal expansion. Next, I have the initial length. In this case, we said that the initial length was 3 meters times the change in temp. And we figured out the change in temp was 90 degrees Celsius. Now, since I have this kind of 1 over Celsius here and Celsius here, I'll find that my Celsius is cancel. And I'm just left with the meters as the only unit, which is what I'm looking for. This math, however, I can't do in my head, so let's go open parentheses, 24 times 10, xy, 6, make that negative, close the parentheses, times 3 times 90. All right, so I got 0.00648, okay? 0.00648. And that's, once again, that's in meters. That's the only unit I have left. Now, that's not the final length. That's just how much this metal rod, this aluminum rod, is changing. So I'd actually find what, I know that change in length is equal to the final length minus the initial length. In this case, if I want to get LF by itself, I'm just going to add the initial length to both sides. So LF is equal to the change in length plus the initial length. Okay, so in this case, my change in length was that 0.00648 meters plus the initial length we said was 3 meters. I need this math in my head, 3.00648 meters. Okay, so that's my final length. A lot of questions are just going to ask you, what's the change in length? Really, this doesn't seem like it's actually changing length all that much. But if we think about it, like that's over half a centimeter. I know, big deal. It's 6.5 millimeters here. But if I'm talking about like aluminum pieces that are tightly packed together or that are butting up against each other, this much expansion would be enough to uh, maybe cause a certain engine part to break. It could have huge effects on like a huge piece of machinery. When it comes to construction, large structures like the Eiffel Tower, where the lengths are, thank you, Flipboard, where the lengths are way bigger than 3 meters, or if it's, let's say that we had 10 of these, all lined up, that's a change of quite a bit. It has huge effects structurally. This whole idea of thermal expansion has major implications when it comes to things like engineering, especially engineering an item that is going to experience some huge changes in temperature, because things will get longer if they warm up. They'll also get smaller if they cool down. So you have to keep that in mind as well. Um, this also helps to explain like a really simple, basic, everyday phenomenon. People that do canning or even if you buy like a jar of pickles or something, the lid is metal, the glass is not metal. And what we're going to find is that typically the coefficient of thermal expansion for glass is less than a lot of metals. So when you cool it down, that metal shrinks more, and so it's going to be super tightened onto the rim of the glass. So the easiest way then to get that lid off then is to run it over hot water. That heats up the metal, allows it to expand, kind of releasing its grip on the glass jar. I just kind of bring this up to an everyday real world kind of thing. Essentially, the equation is not horrible. I mean, it's kind of a four variable equation. Everything's pretty straightforward, and one of them you just kind of get straight from a chart that you should have access to. Other than that, good luck with the practice, and yeah, talk to you later.